Hey everybody, this is Larry. This is me going Q4 of the weekly contest 469, number of ZigZag arrays 2. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and everything in between and so forth. This one, before I start, I want to say, Q3, at least for the explanation part, is a prerequisite of this. Because, well, just to be frank, I am lazy and I don't want to repeat everything that I said in Q3. So understand that, at least understand the video a little bit and then come back, right? I mean, there's nothing wrong with it, and I don't think you necessarily need to know Q3 to solve Q4, because even though they are similar problems, and knowing stuff in Q3 does help with Q4, but it's not necessary. But I just want to, I want you to watch that, or at least understand it, and if you think you understand it, that's fine. But I want you to understand it to a point so that when I show you certain things later on, you won't be like, oh, Larry didn't explain this. Well, listen, if I didn't explain this in the other video. But in any case, yeah. So let's jump right ahead, assuming that you understand Q3 and the solution, right? And not even the optimized solution, you could just do the unoptimized solution, right? And during that video, I do talk about the unoptimized solution, which is this one, right? Which is the really brute force one, where you have three states, you have the current number, you have the numbers. You have number of numbers left, you have increasing whether it's true or false, right? And then now we talked about how there's 8 million inputs, but that's for the last one. So actually these parts are now relevant for this one. And of course this isn't even 2000. But of course this solution is not fast enough for this problem. We don't have to prove that. You probably have a good intuition. Otherwise you just submitted it, right? But this is kind of the idea behind Q3 in a brute force kind of way. And for this one, it is a matrix exponentiation problem. A little bit of a spoiler. It's really hard to kind of get into the explanation of it without having that background as well, and also that is entire lecture of. But basically, matrix exponential, or even just matrix multiplication in terms of graph theory, right? Oops. So not just like a regular matrix thing, but a graph theory thing. But one of the things that it enables you to do is, I mean, it's a little bit graph theory, but it's actually more linear algebra. Maybe I lied on this one, right? But the reason why I say the graph, there are some graph theory components about it, about transition edges and stuff like that. But maybe linear algebra is the better way to explain it. And what I mean by that is that now, let's just say you have a node, right? You have a node where the node is current left increasing, right? Yeah. Well, looking at this function, what does it mean, right? Well, you know that left always depends on left minus 1. So you could kind of, that already gives you a visualization of, okay, you have a set of nodes. I do want to bring up the paintbrush, but I don't know if it helps too much. Because I just want to say, there's a bunch of nodes. I'm just going to draw some circles, right? Okay, actually, let me just do it anyway. Hang on. Right. Sorry, let me... Okay, so for this problem, right, you have a bunch of nodes. Oops, what did I do? So for this problem, we have a bunch of nodes. Right. Oh man, I clicked on some other thing. Why is this thing so weird? Okay, so you have a bunch of nodes, right? And these nodes is actually, maybe for this one, it is, again, we'll just say C is equal to current, L is equal to L is equal to left, and then you have increasing or not, so I for increasing, right? And keeping in mind that the way that I would maybe draw it this time is that this is L, so all these are in L, and then this is maybe L minus 1, right? And the reason why is because then now you could draw the cells as we previously did, but in terms of nodes, right? Because if you remember our Q3 matrix visualization, this is the same thing kind of, except for it's with nodes. And as a result, you can kind of think about it as like, for example, maybe you have this, which is CL, and for some I is equal to some, is equal to the sum of this node and this node, say, right? And maybe this one is equal to the sum of this node, and this node, because it's still, I mean, there's like this prefix sub type structure, but it's not actually important for this particular Q4. But, you know, but you could kind of see how this is, you know, this is the sum of this and this and this and this, right? Okay, so then now what? Let's just, for fun, let's label this in a different way. Let's label this, you know, now we have to figure out how to connect these edges, but keep in mind another thing though, right? Is that let's just say there's an L minus 2, right? Well, it turns out, and I am kind of hand wavy over the increasing part because it's too much dimensional. We'll go over it in code, but let's just pretend that we always go for the smaller part, right? So that means that here, this node goes here. This node is the sum of these two. This node is the sum of these two, these three. And if you kind of compare these edges and these edges, they are exactly the same, right? I mean, again, I'm ignoring the increasing part, right? Because it's not. I just want you to kind of build the intuition and the visualization, and I don't have a three-dimensional thing to, you know, like, I don't know, Minority Report or something, you know. But yeah, but basically you have that, right? And now let's do something a little bit different. Now we're assuming the edges. So that means that, let's say we have A, right? A of L, B of L, C of L, D of L, E of L, right? And then underneath you have just A of L minus 1, B of L minus 1, ... right? You can figure it out. And in this case, you could say that B of L is equal to A of L, right? And C of L is equal to A of L plus B of L. And then D of L is equal to A of, oh sorry, it's A minus 1, my fault. A L minus 1 plus B L minus 1 plus C L minus 1, right? So the previous level, but you know, all these prefix sum, right? And you can set this prefix sum, you know, it looks pretty straightforward, but the key thing to note is that now, let me erase something. Now that you have this formula, these formulas, you can now represent them in terms of a matrix, right? Because now you're saying that yeah, now you have a matrix. How do I say it quite precisely? Because I have the increasing version in my head, that's why, right? So now you're saying, you know, A sub L, B sub L, C sub L, D sub L, ... is equal to, well, A sub L is just equal to 0, I suppose, if you kind of want to put it that way. But then B sub L is equal to 1 A sub L minus 1, and C is this, right? So you have kind of like this matrix, right? And then it turns out in graph combinatorial theory, and maybe I drew too many zeros, whatever, is that, so this is every transition, right? And technically speaking, it doesn't have to be an exponentiation, right? Because what we said about the edges earlier, we said that all the edges from from level L to L minus 1 is the same as L minus 1 to L minus 2, right? But if they were not the same, then maybe, you know, maybe you have another, so this is, maybe you could say M sub L is equal to this thing for the transition, or maybe T sub L for the transition, I don't know. Whatever, M sub L is equal to this, and then L minus 1. Let's just say, for argument's sake, for just visualization, this is different, right? I don't know. Like, it's just random numbers, right? And assuming that they have the same size, because obviously if they're not the same size, you can't really do it. But then now, if you want to know what happened, if you want to do the count, you could kind of just write out these formulas, And the TLDR, I'm skipping a little bit, and this does require a little bit of a linear algebra background. There's a lot of proofs. I'm not going to do all that because it's too much first principle. But basically, you can say that m sub l times m sub l minus 1. Actually, I don't know which way it goes. I may be wrong on this because maybe they're going the wrong way depending on which way you count. But in either way, it's one of those things where then now this is equal to the same as applying this and then applying this afterwards, or maybe the other way around. My fault. But in any case, for this particular problem though, m of l minus 1 is actually equal to m to the l, right? Because the transition matrix don't change, and as a result, right? And hopefully I made it clear that you could transform these formulas into a matrix. Maybe that part I was not clear on. But like I said, that is where you need the linear algebra background, to be frank, to kind of But once you see the pattern, you convert it to a transformation matrix, and then now you have m l minus, and of course not only this, m l minus 2 is equal to m l as well, right? Dot dot dot. So that means that they're all the same m. Right? It's the same transition graph. And then now, to do this, so that means that to do this 10 to the 9 times, which is way too big, then now just m to the n minus 1, or whatever m it is, or l minus 1. Sorry. And that's it. That's basically the core idea about converting this into a matrix exponential problem, or solution, if you will. Yeah. And of course, it's a little. We'll go over the nuance about increasing and decreasing, but I just want to get you the idea, the framework on how to build it. And I know that I did a little bit hand waving a lot of bits, but each of those bits, like if you really want to be precise and first principle, is like 10-15 minutes, and then listen, I don't know. I'm exhausted. All right, but in any case, yeah. Okay, so the difference between what we said is that there is this increasing and decreasing. So, but let's remove left from now, or not consider left, right? Then that means that, well, how many possible states are there? Well, not including left, how many transitional things are there, right? Well, left can go from 0 to n, as we said, and increasing is 2. That means that you just have 2 times n number of states, right? And that also means that you have basically, it will just go from 0 true, 1 true, 2 true, dot dot dot, all the way to I guess I will n. So like n true, and then maybe 0 false, 1 false, dot dot dot, all the way to n false, or n false, right? So here you have 2 times n states, and then now, as a result of just drawing it, is that the increasing states will connect to the on the previous level, the increasing states, the true states, would connect to the 4 states, and the 4 states will connect to the true states. And that's basically the idea, and you have to kind of make sure that you connect them correctly, if it's increasing, the number should increase and so forth, right? We'll go over the code, don't worry. But I just want you to kind of think about these separating them and then compress them, right? Because in the sense that you could think of these as 2 dimensions, right? One is the true force, one is n. But if you kind of unroll the dimensions, then now you have 2 times n number of states. And then now compress it back to 1 dimension. Then now you have 1 dimension where this is the mapping. That's basically what I want to do. And that's basically what I end up doing. I'm going to skip the matrix multiplication math. You could just Google this, really. I have this as a template from somewhere in the past. You have to keep in mind the mod, because it gets too big otherwise and too slow otherwise. The power as well. This is I'll go over this very briefly, why we want to do math power. But basically, it's just that if I guess I should have talked about this a little bit. But m to the n, right? If n is equal to 10 to the 9, you cannot just do m times m times m times m, dot dot dot. This is going to be too slow. But instead, it is just the same thing with matrix with regular numbers, right? So you can do m to the n is equal to, roughly speaking, m to the n over 2 square, right? Oops. so that's basically it. And there's some stuff about odd numbers, etc. But as a result, that means that you divide it by 2 every time, and then you do only one multiplication, which is the square part, after dividing by 2. So that means that for n is equal to 10 to the 39, you only do this multiplication 30 times, maybe 60 times because of the odd, extra due to odd. But yeah, but I'm not gonna go with that in detail. That part, you could Google it up on your own time. Not even matrix part, just like regular number, repeated doubling, repeated powering, whatever you want to call it. And there's this vector thing, which is maybe not necessary, honestly. At least the way that I set it up, it was not necessary. But I just wanted it there for debugging reasons. And then yeah, so then here, as I said, as I did in Q3, we compressed the thing from L to R to 0 to R inclusive. And then I just have a number T, which is R times 2. This is what we talked about here with all these states, right? Yeah, so then now the first R is increasing, and then the second R numbers, first R numbers, maybe put that way. Indexes maybe. So we set up a matrix from T to T, and keep in mind that T is equal to 150, right? Because R is equal to 75, right? So yeah, 150 square. We'll go over the complexity afterwards. But yeah, for each I, we go, well, yeah, so we connect the increasing ones to the decreasing ones. And it's not, I say connect because it's not quite precise. I think of it as a graph, but that's because it's a relic of the fact that if you kind of look at these formulas, right? All these, the constant here is 1, right? Where's the C? Oh. And because the constant here is 1, it maps to these ones here. But you can imagine that, and this is just for future learning purposes. For example, if B sub L is equal to 5 times this, then this would be a 5, right? And maybe it'll be like 25 and a 5 or something like that. I don't know. But you could imagine that that'd be the case, and you have just different numbers in the matrix. So it's not always a 1. It's not, yeah. In this problem, the setup makes it a 1, but it's not necessary. But in this case, you can see that the increasing numbers maps to the decreasing number, which is a 1. We have the decreasing numbers, the same thing. And keep in mind that J goes from higher I's, and in this case, in the decreasing case, J goes to lower I's. And you get I to J, mapping the increase, decreasing. This is to set up the transitional matrix. And then now we just go to the power of n minus 1. I actually kind of was a little bit sloppy when I was doing the contest. I just go to n, but it's n minus 1 because the first one is just applying it from the first time from the identity matrix. So, okay. Right. Anyway, and then you could, it's actually good enough to kind of sum the matrix because these are all ones anyway. So it just, I don't know, this is actually very unnecessary to convert it to a vector, but you could just sum the matrix and then just remember to mod at the end. And that's it. What's the complexity here, right? So matrix, so M or T, whatever, just got M is equal to 100 by 150, right? So matrix multiplication, right? Each multiplication is equal to 150 cubed, right? And we do at most 60 multiplication, as we said, right? Because for the because if it's 10 to the 9, that means that we get to divide it 30 times because of binary bisection type things. But of course, if it's odd, then you have to multiply one more because okay, I could write it out here, right? So if n is even, that's the case, right? If n is odd, then it's actually m is equal to this thing times m, right? Because this is divided by 2, and then you're off by 1, so you have to times it by m, and this is a matrix multiplication. So you have so you have at most 2 matrix multiplication per core. You have 30 core, or yeah, you have 30 cores, so that means it's 60 matrix multiplication at most. Let's make that clear. Maybe one more for vector, but you can and just sum it, right? And so as a result, that is just 60 times 100. You can also say that maybe R, or this isn't the input R, is the delta R, but it's at most 70. Yeah. So it's going to be O of 2 times R times log of, what is it, N? Yeah, N, right? Log of N, where N is the input, not the input size. So it's a little bit awkward, right? And so that, so this cube, right, is your total complexity. And that's it. Yeah. And of course the 2 kind of, goes away in the thing, but yeah. And that's it. That's all I have with this one. Let me know what you think. Thanks for watching, and I'll scan over the code real quick, make it a little bit smaller, maybe helps. This is the top in case you want to know the brute force way. I talk about this in Q3 in more detail, but yeah, the matrix multiplication code, pretty standard. I probably copied it a long time ago. I mean, I wrote it, I have it written before as well. So I usually put the IJK in different order, but I don't know. I don't know why I did it this way. But anyways, mod pow, straightforward. Vector multiplication is also straightforward. And then yeah, and then now this fits on the screen, even with the comments, and that's it. That's all I have with this one. Let me know what you think. Thanks for watching, and you can watch me solve a live in contest now. I hate Leetcode. 200 people got this, and I have about 40 minutes to go. I don't know what to say, right? Like, I solved this like an hour ago. You gave me like 4 penalties and a lot of time, so I don't even know anymore. But apparently there is a, better way to do it, maybe. Well, obviously go to 75. I don't even, my brain juice is just off because I used all of it on that damn problem. It wasn't even that hard. It's just that Leetcode has some ridiculous timing things. I mean, I was dumb at some points, but all right. I mean, this could be a good problem too. It's just that I'm like so far behind because of it. All right, how did I think about it? 75, 75, 75. Oh, n is really big. N is not 10 to the 6. I thought it was just 10 to the 6. N is actually really big. But 75, 75, 75. So it's like it's probably an exponentialization problem, right? Yeah, okay. That makes sense then. Actually, it's not that bad then. Okay, yeah. Then now we need a transition graph, right? So, okay, we do the same thing as before. This part, I mean. The sad thing is that this Q3 was not that bad. It's just that Leetcode is dumb. Okay. Okay, so then now okay, let's think about this. Oh, not this one. Not even this one, really. I mean, it's fine. Was this the wrong answer one? Oh, this is the wrong answer one, but where's my... Okay. So this is my... Where is my... So this is my code. But that's already optimized. You could say not enough, but actually the way to think about this, and this is doable, but I have to... okay, so then now this is actually right? So Okay, so if increasing is not 1, then total no, that's it, right? Oh no, increasing is 1, right? So something like that. Right, okay, so that's the graph. So then now there's 75, 75. Oh no, well now left is no, left is fine. So then 75 times 3, I suppose. Is it right? Let me double check something real quick actually. I mean I did it this way, but do I need to? Do I just do maybe plus why is that good enough? I mean it fits the example. I'm just YOLO submit because it doesn't matter. Okay, so that means actually I could remove the dimension, so it's even better. Which maybe is what I needed to optimize. I didn't really think about it. Maybe that does do more work, this one. But maybe I'll do it after the contest to optimize. We have half an hour to go. And then now, that means that, yeah, so that means that we have a matrix. Okay. We have the transitional matrix, which is and the initial thing, right? Okay, maybe I don't need. I mean, maybe I should have known this, but I can't think anymore. So I'm just trying. Okay, right. Let's just say 0 for. So left minus 1. So you have 75 plus 75, or R times R, right? So T is equal to, I don't know, R times 2. Yeah, 1 for increase, 1 for decrease, right? Right, so then now it's going to be for I in range of R. Okay, so this is increasing, say. So then now this is actually I plus 1. So then now I. No. It's the reverse, right? So it's going to be T plus J is equal to 1. Or the other way around. I don't know. No. This is increasing, right? So if we want to do decreasing, then this is actually. I mean, that's fine, I guess. Is it like this though? Something like this. And I wish I had more than half an hour because this is doable. It's just okay. So the first half is increasing. Okay, just write down. So now in increasing, we take a look at the decreasing. Decreasing, we take a look at the increasing. So okay, that's where I was trying to figure out. Okay, and then now yeah, and then now we just have, where's my I have my code somewhere. Okay. Is that okay? I probably could win it. I usually write this recursively actually, but okay. So we want to map pow mat n. Oh, of course there's a mod into that. That's right, because you never really win. Okay. I guess and the answer is that you can actually multiply it just by a matrix, but we can also just sum it up, right? This isn't quite right. No, this is right. So that means that we want to do let me just print it out real quick. Yeah, okay, fine. I just want it. This assignment, Y. Oh no, it's not T, it's R. Oops. Obviously, maybe. So this is 2, is that right? 5 plus, this is just 8. Is 8 right? No, it's 10, right? So how can I convert this to the answer? And it's just like a mirror thing. Am I right? I mean, the idea is right, but am I setting it up wrong? I mean, for symmetry reasons, it should be pretty right. But let me. I guess I should have just copied all of it. Yeah, I mean, that's what I thought. And this is fine, but this is not, right? This is 16. Is the, it's not quite right. Let's do it without the power first. So what is this saying? This is saying that the 0 number, if it's increasing, it goes to the decreasing, or it counts from the decreasing, right? The idea is roughly right, but I'm not doing it right at all. Or is it maybe that I did it the other way? Maybe, okay, let's try the. I mean, why not? No, it's just in a symmetric kind of way. So maybe, so one of these is wrong. I mean, well, it's symmetric, and I guess I'm saved by the symmetry, but that doesn't make it right. I like that way a little bit. Oops. That means I don't know how. Maybe I don't know how to do it. Maybe I lied. Okay, let's try n is 0 to 1 actually. Maybe I'm off by 1. That could be it. Let's just say n is 1. I cannot edit it, even though it looks editable. Oh, at least 3. Why is it at least 3? Okay, let's just try. I guess that cannot be 1 because I just 0. All right, let's see if that works with 0. Okay, at least 2. Okay, fine. Oh, and they have to be greater than anyway, so I'm wrong on that one. Okay, let's just say 1, 2. That's the simplest case. And then it's just 1, 2, and 2, 1, right? No, it's 1, 2, 1, and 2, 1, 2. Well, I guess that's just the first case. How do you get 10? I don't really need this anymore, maybe. I just need to figure out how to do it. Oh, and also I need mod here just in case. But I mean, this is fine, but how do I get the example? But the 10 part is not working. Am I just like multiplying 1 extra? Well, maybe I am just multiplying 1 extra. What's a test case in here that I was wrong on? Not this one. 4, 16, 20. Okay. Okay, so that looks okay. So let's YOLO submit. Okay, I was going to just remove the print, but that would be pretty bad. I actually thought about the n-1 thing, but then I just forgot about it at some point. Oh. Hopefully I didn't make any silly mistakes, but I mean, I don't know. If it times out, I would have to do some maths too. Why would it time out? 75 cube. I mean, it didn't time out, but I don't know. I'm not really happy about this. I mean, thanks for watching, everybody. Hit the like button, hit subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.